Kia ora. For our fourth tip, we're going to identify the reactive site to help us make sense of organic reactions. So here what you do is you look for the functional group. So for example, if we use these three examples, the functional group, it's alkane, carbon-carbon, single bonds, carbon-hydrogen. Here it's the alcohol, here it's the carboxylic acid. The next step is look at the electronegativity of the atoms bonded to that carbon. So there's not much difference in the carbon and the hydrogen, and overall it's considered pretty much nonpolar, but there is a difference in the oxygen and the carbon, 2.5 and 3.5. So this carbon is fairly electron poor, and this one is even more electron poor because you've got electron density being dragged off to the oxygens because they are more electronegative. So alkanes, very little reactivity. They basically just burn, combust, and undergo slow bromination. With the alcohols, they can be attacked by nucleophiles. So nucleophile means loving, nuclear positive. So it's positive loving stuff. So for example, it has to be electron rich like a chloride because they're negative, so they want to go to something positive. And the same thing over here, attacked by nucleophiles. So they can also undergo other reactions, and we'll look at examples in the next slide. But the first thing you need to think of, which bonds will break. So if this undergoes substitution, so something's coming in here, this carbon has got 4 bonds, so one of them must break and go. Now carbon-carbon bonds and carbon-hydrogen bonds are pretty strong bonds because of these they're pretty much non-polar. The more polar the bond, the more easily it can break. And so it's likely that it's going to break here rather than a CH bond being broken. So the OH will come off rather than any of the methyl or the hydrogens. Here, the double bond is much stronger because it's a double bond, so twice the number of electrons holding it together. So that's unlikely to break, and so it will break over here, the CO bond being broken, rather than the C bond. So here are some examples. So in the secondary alcohol, again, look at where's the electronegativity difference, or the functional group electronegativity difference. So the nucleophile will attack here in terms of a substitution. However, it will also undergo elimination or oxidation. So why elimination? Look at the reactive site. It's this carbon. So we've got these adjacent carbons, each having hydrogens. So if I remove this OH plus the adjacent hydrogen, I can undergo elimination. Oxidation, it can do this because my reactive site of carbon has a hydrogen over there as well as there. So I can remove hydrogen to get it oxidized. Over here, again, I have a polarization of the bond, and therefore I will have nucleophiles attacking this slightly positive carbon, and it can undergo substitution or elimination. So substitution, when the chloride leaves, and something else comes in that's rich in electrons, like an OH minus, for instance. And elimination is because my reactive site carbon is bonded to another carbon that has hydrogens on it, so I can have one of those hydrogens go together with the chloride to form an alkene. Now, alkenes are electron rich, so they don't get attacked by nucleophiles, they get attacked by electrophiles. Because there's lots of electrons in this area. I suggest, though, you just simply learn the undergo addition and you just learn the reagents because it's not quite so easy to work out. Aldehydes, we've got a carbon-oxygen double bond and a carbon-hydrogen single bond that's been made a little bit weaker in terms of the bond because of the strong electronegativity up here, just pulling electron density away from the carbon. So yes, it does undergo nucleophilic attack, but we don't do that at NCA level 3. So we're just looking at reduction. We can reduce it by adding adding hydrogen to this oxygen and another hydrogen to the carbon. Remember, we can break that bond into a single bond, and then we can add a group to each one. Oxidation, we can remove this hydrogen and add OH minus in its place. So it can also undergo oxidation. Finally, the ketone. Again, we could have nucleophilic attack, but you don't need to know that. So you just need to know reduction. So we can, just like the aldehyde, we can add an hydrogen to this oxygen and the other hydrogen to the carbon, but it can't undergo oxidation. And if you think about it, I don't have a hydrogen to remove. I can't break a carbon-carbon bond. So therefore, ketones do not undergo oxidation. All the best. Kia ora.